We're at a bit of a milestone today. This is our 10th lecture for CIVE 360. Let's take a look at what we've done so far with most of our time. I would say that our discussions thus far have been dominated by the practical example of the axially loaded bar. So this is a 2x4 piece of rebar, something that is long, it's relatively thin, and it resists the load by stretch. So from this particular solid, the axial bar, we have a sigma is equal to P over A. And normally when we say that, it means we're assuming that there's a cut this way. And we found that that actually is the cut that gives us the largest normal stress. Remember, the maximum normal stress is P over A, and it occurs when our cutting plane is perpendicular to the direction of the load. So that's going to be typically the governing normal stress that we have for most of these axial bar problems. And then as long as everything is constant, we found that delta is PL over AE. There's a lot of problems that are actually governed by this basic mechanics process. And we won't bother going into that right now, but you'll see some of those later in your career. And kind of the pinnacle of our study so far has been the statically indeterminate sequence. So if you can understand the three types of statically indeterminate axial bar problems that we have so far, then you know how to approach those and you know how to set up equilibrium, stress, strain, and compatibility, then you're in pretty good shape. We're actually going to now take a little bit of make a little bit of a shift in our analysis, and we're going to introduce a new topic, and this is typically known as torsion. So that gets its own big heading. And torsion is actually a deformation process. What is it? Torsion is the way that a solid deforms to resist torque. So it is a type of deformation that resists torque. In fact, a lot of people will use the words torsion, torque, twist, kind of interchangeably. Normally, torque is the load. Twist is the displacement. So we get an angle of displacement, and then the torsion is actually the type of deformation that we get. So twist is typically an angle of twist, whereas torsion really refers to the global process that's going to be occurring. So a typical example would be I've got a piece of this foam rubber that's supposed to be for rehabbing your tendons, and it looks like this. It's about 1 inch in diameter, about 6 inches long. And we, in my case, it's corrugated circle, but we'll assume that it's a circle like this. And we apply a torque to it. Now, the way that I typically write a torque is by using the double arrow nomenclature. So a double arrow means that it's a moment. So we've got a twist here and a twist here. So it'd be like taking your pencil or a piece of chalk or my tendon rehab, and you're twisting it in equal and opposite directions. The nice thing about this particular solid is that it's going to really generate one dominant type of stress, and we'll elaborate on that as we make our way through. So our two key questions, once again, two questions. One, is it going to fail? And the failure then is going to be dominated by the stress. So we really say, I'll go ahead and say, will it fail? And I'll put inside here the stress. And the second thing that we want to answer as solid mechanicists is, how much does it twist? So how much twist is there going to be? So normally if I had a vertical bar sitting up like this and I twisted it, then it would end up like this. And that is typically what we want to know. So theta is then what we're going to get as the angle of twist. In this case, it would be relative to the right-hand end of the bar. So how much rotation is there going to be as we apply that particular load? As we work our way through our applications, we're really interested in two types of solid. So two types of solid that's going to be subjected to a twist like this. The first, and it's really going to be the one that we're going to spend most of the time on, is a circular cross-section. Now, we don't have time to study and analyze more than the circular cross-section, and they get complicated really, really quickly. But there's kind of an amazing thing about the circle. First off, it is the easiest one to analyze. So I'll put that in scare quotes. It is easy to analyze. That's relative, of course. I mean, it's going to take us a little bit of work to go through it, but compared to some of the other sections, it really is straightforward. So it's fairly easy to analyze, but the other thing is it is an extremely good structural section. I'm just going to say it is a great section. What do I mean by that? I mean that you get relatively low stresses and relatively low angles of twist for some value of the applied torque. So it is an extremely efficient section. That's why you see so many structural elements that are going to be loaded in torque that have some sort of circular section. So I will say the circle totally rules, as your grandparents used to say. All right, so the circular cross-section, it's going to occupy a lot of our time. There's another one that on the surface looks extremely difficult to analyze, and it's actually quite a complicated process, but there is a bit of jiggery-pokery that we can invoke to make the analysis really simple. And this turns out to be what is called the thin-walled hollow section. That one appears difficult, but it turns out to be not easy, but it's doable, and doable by us, giving the background that we're going to be able to develop for this. And the thin-walled hollow section, so here maybe we should put on the circle, it looks something like this. And I can draw like that, because that little mnemonic is going to represent three things. That can either be the hollow circle, it could certainly be a solid circle, and then it can be a composite circle. So we could have a core shell type of solid and so on, but it's got basically a circular shape. The thin walled can be anything. It could be, it could look like a house. Something like this, as long as it's formed of a thin wall, something like this. So you've seen sheets like this at Home Depot. You could go look at a hollow PVC pipe. That would be a hollow circle that's thin walled. There's a lot of structural elements that have this sort of character. All right, so what we're going to do, as we always do, is we want to bring it back to our hierarchy of variables. So recall, we want to keep this in the forefront of our minds. Remember, in this class, we go from displacement to strain to stress to force. That is a general idea. Now, we have already introduced the type of loading that we have. For us, so again, this is our general diagram. But for us now, we're going to take this section and twist it with an applied torque T. And that's going to give us our displacement that we care about, which is going to be theta. So if I apply a torque, it causes twist. Now it turns out that that twist is going to cause not a normal strain, but a shear strain. It's going to cause a gamma. That gamma then, when we link it with our constitutive law, is going to cause a shear stress, tau. And when we integrate the moment that shear stress creates about the center, that's going to generate a torque that resists the applied load. So it turns out that for this problem, that is going to be the sequence of force to deformation and then our variables on the in-between. So what we're going to do is start here. This is our starting point. Because it's not as simple as just the axial bar where we pulled on it and we had the delta and so on. It's going to require a little bit more analysis. All right, so we're going to consider then, for right now, we'll consider a solid section. So consider a solid circular cylinder. And let's say that the radius is equal to C. And Normally that's a funny way of having the radius, but that's going to be the outermost radius, and we're going to see that we're actually going to ditch that relatively soon. So it looks something like this, and then it goes down here, and down here. There it is. And so the outer radius then is going to be equal to C. And we're applying our torque to it. So I'm going to move the torque arrow out a little bit there and there. So after deformation then, we are going to have this segment then move to some sort of new position. Now what we want to do is list a number of kinematic assumptions that we're going to make. So we say our kinematic assumptions. And remember, anytime that we use the word kinematic, we're asking, how does it deform? How does it move? And so what we're going to do is we are going to make and state a number of assumptions about the way that this particular solid deforms under an applied torque. We'll go ahead and put the T there. And if we have a T there, then we also have to have a T here. So we are going to make a number of kinematic assumptions about how this deforms, and somewhat incredibly, the simplest possible explanation is the one that's correct. So note, we choose the simplest mechanism possible. And it turns out that it is correct. It's not always the case, of course. We may assume that there's a simple mechanism that explains something, but it turns out not to be the case. If you've taken a class in philosophy, you may have come across something called Occam's razor. It says if there's a number of competing explanations for something that happened, the simplest one is almost always correct. So this is going to be a Occam's razor type of deformation, and we'll state that what that was in part 2.